As we just saw in the terminal, this script pulled live weather data, calculated a factorial, and searched the web for a recent Super Bowl winner. How does a language model break out of its text box to do all of that? This diagram outlines the difference. Standard language models are stateless. They take an input, give an output, and immediately forget the interaction. An AI agent, however, runs in a continuous loop. We structure this loop using the ReAct pattern, which stands for reasoning and acting. The model generates a thought about its goal, executes an action using an outside tool, and then receives an observation back. This looping structure is what allows the AI to handle a request like check the weather and then calculate the temperature difference without a human needing to copy-paste results between steps. To give our agent actual abilities, we write 3 Python functions, one to hit a weather API, one to parse math safely using the numexpr library, and one to search DuckDuckGo. But writing the code is only the first step. A language model API cannot natively read your Python file to figure out what these functions do or which arguments they require. This visualization maps the solution. We translate each tool into a JSON schema. This schema acts as an instruction manual, telling the model the name of the tool, its purpose, and the parameters needed to trigger it. Structuring these definitions provides the required syntax for the model to request a function call, bridging your local code to the AI. This flowchart represents our Python architecture. A central while loop orchestrates the back and forth between the model and tools. Before running, we build a hard limit, a max steps variable. This gate prevents the agent from getting stuck in an infinite loop and burning API credits. Think about this. Standard language models have no memory. After the agent runs the weather tool, how does it know the temperature when it goes to calculate the next step? Here is the core mechanism. Every time a Python tool finishes running, its text output, the observation, is appended to the conversation history array. The updated stack is then sent back to the model for the next turn. By physically feeding the results of every action back into the context window, we simulate short-term memory, allowing the model to chain multiple steps together. Let's trace our original prompt. The model outputs a thought, generating an action for the weather API. The script logs the observation. The loop triggers again to calculate 5 factorial, and a third time to search the web. With context filled, it prints the answer. To keep this tool calling environment consistent, we wrap the script and its dependencies in a Docker container. This ensures that the weather and math tools work the same way regardless of your local setup. To build a ReAct agent from scratch, you rely on this architecture. Write your Python tools, define their JSON schemas, implement the loop, append observations to the context window, and cap it with a max steps limit.